Hydraulic Actuation Systems Part 3. In this we are going to discuss hydraulic pumps, the pumps used in hydraulic actuation systems. Hydraulic pumps. The pump converts the mechanical energy of its prime mover to hydraulic energy by delivering a given quantity of hydraulic fluid at high pressure into the system. Generically, all pumps are divided into two categories, namely hydrodynamic or non-positive displacement and hydrostatic or positive displacement. Hydraulic systems generally employ positive displacement pumps only. The symbol for a pump is shown in figure 26.8. Request. It is hoped that this lecture is going to be useful to you. Please press like. Please subscribe. Hydrostatic or positive displacement pumps. These pumps deliver a given amount of fluid for each cycle of motion, that is stroke or revolution. Their output in terms of the volume flow rate is solely dependent on the speed of the prime mover and is independent of outlet pressure, notwithstanding leakage. These pumps are generally rated by their volume flow rate output at a given drive speed and by their maximum operating pressure capability, which is specified based on factors of safety and operating life considerations. In theory, a pump delivers an amount of fluid equal to its displacement each cycle or revolution. In reality, the actual output is reduced because of internal leakage or slippage, which increases with operating pressure. Moreover, note that the power requirement on the prime mover theoretically increases with the pump delivery at a constant fluid pressure. If this power exceeds the power that the prime mover can handle, the pump speed and the delivery rate would fall automatically. There are various types of pumps used in hydraulic systems as described in the following slides. Gear pumps. A gear pump develops flow by carrying fluid between the teeth of two meshed gears. One gear is driven by the drive shaft and turns the other, which is free. The pumping chambers formed between the gear teeth are enclosed by the pump housing and the side plates. Inlet as the gear teeth separate. As a result, fluid flows in and is carried around by the gears. As the teeth mesh again at the outlet, high pressure is created and the fluid is forced out. Figure 26.9 shows the construction of a typical internal gears pump. Most gear type pumps are fixed displacement. They range in output from very low to high volume. They usually operate at comparatively low pressure. Vane pumps. In a vane pump, a rotor is coupled to the drive shaft and turns inside a cam ring. Vanes are fitted to the rotor slots and follow the inner surface of the ring as the rotor turns. See figure 26.10. Centrifugal force and pressure under the vanes keep them pressed against the ring. Pumping chambers are formed between the vanes and are enclosed by the rotor, ring and two side plates. At the pump inlet, a low pressure region is created as the space between the rotor and ring increases. Oil entering here is trapped in the pumping chambers and then is pushed into the outlet as the space decreases. Balanced vane pumps. Most fixed displacement vane pumps today utilize the balanced design shown in figure 26.11. In this design, the cam ring is elliptical rather than a circle and permits two sets of internal ports. Two outlet ports are 180 degrees apart so that pressure forces on the rotor are cancelled out, preventing side loading of the drive shaft and bearings. Piston pumps. In a piston pumps, a piston reciprocating in a bore draws in fluid as it is retracted and expels it on the forward stroke. Two basic types of piston pumps are radial and axial. A radial pump has the pistons arranged radially in a cylindrical block. In an axial pump, the pistons are parallel to the axis of the cylinder block. The latter may be further divided into inline and bent axis types. Here the further details are not being discussed. Request. It is hoped that this lecture is useful to you. Please press like. Please subscribe.